So today we'll continue the work on the positive cone. In particular, I think David last time computed the pure states, the extreme rays, which is basically when you cut it with a normalization functional, you get the pure states, the extremal states. So those are rank 1 operators. Then I think he computed the extreme effects, that is operated between 0 and 1, that can play the role as yes-no measurements, and started talking about observables, right? So we look at extremal observables. And now, again, of course, an observable is just a collection of positive operators, which is normalized, a finite set of outcomes, let's say. Okay, so, and that's a convex set because I have two observables on the same outcome set. So then of course, by taking convex combinations of these operators for all A, the same weights, I immediately get a new observable. And the interpretation, as always, is statistical mixing, randomization. Right? So if I have two given observables with the same outcomes, I flip a coin which one I want to use. And then I get, of course, I use that observable, I get an outcome. And that's the statistic of my combined mixed observable. Right? Okay, so why are we interested in extremal ones? Because this mixing process introduces additional noise. So we would like to see optimal observables, good observables, that tell you as much as possible. So which are the most informative ones in some sense? Right? So there's least apparatus noise in the game. Now, it's therefore natural to look at I think we call that the finest observables. So just think of one of these operators being split into two other terms. Right? So A is, this outcome A would therefore be split into one A prime and A double prime. So let me write that. So FA is FA prime plus FA double prime. Right? If you have such a splitting, and these are not proportional, then the resulting observable will tell you more, because you can simply come back to the old observable by forgetting that distinction. Whenever either A prime or A double prime is an outcome of the observable that you get this way, right? Then you just forget the primes, right? And then you have a completely equivalent measurement as you had before. So you always get more outcomes out of this. You get more. It's more informative. There's one case where this doesn't really help. Namely, when FA prime and FA double prime are proportional to FA. What happens in that case is that you get a finer distinction, but the difference is really only flipping a coin, right? Because these two are equivalent, and so they basically are always proportional with the same proportionality function, and therefore you get. It's just like flipping an extra coin and producing an extra result this way. So this is not interesting. So this split makes observable more informative. Unless FA prime is some lambda times FA, and then of course the F double prime would be 1 minus lambda FA. And so then it's only this additional information just amounts to an additional coin toss, right? And this doesn't really help. So, but this condition splitting as long as you can until you hit operators that you cannot split in a non-trivial way any further, is exactly looking for the extreme rays. Right? So we're just going for the extreme rays of the cone. So if any one of these FAs is not extremal, you can do the splitting and get a more informative observable this way. Right? And this is why we're interested in the finest ones. So consider only the case where FA is on extreme ray for all A. So you can improve an observable as long as that is not the case, and so let's just take the best ones. Right? And of course we know what the extreme rays are. They are just the proportional, they are, I mean, each ray consists of the multiples of a one-dimensional projection. Right? So, so then the proposition or theorem or something consider an observable with let's say the rank of FA is 1 for all A. This is exactly saying it's a finite, one of these finest things. Right? Then it is extremal. If the FA are linearly independent. Okay. So, how does this work? I think David mentioned the theorem. Is that correct? He was sort of heading towards it, at least. That's what he told me. Right? So I'm not sure he stated it in exactly this way. So let's look at a proof. So suppose that f is lambda g plus 1 minus lambda h, let's say. And which just means, as written as an equation for observables, this means that this is true for every element. Right? So, but the lambdas don't depend on A, right? So they're just you do the mixing before you get the outcome. That's one way to say it. Okay, so suppose that we could actually decompose that. What would that mean? Right? Now, it's clear that. So because f is on an extreme ray, it would follow that GA is actually some multiple of FA. And similarly, HA would be some HA times FA for some GA, HA, which is positive. Right? So this is the extremality that just kicks in here. So this operator, the first term here, is clearly less positive, right? Because G is an observable, and it's less than FA because I dropped the term. So therefore, it must be proportional to this to the element FA. Right? Okay, so this is actually useful for both directions of the proof. Now we have to show that if the FA are linearly independent, So assume this now, and we have to show that on that condition, G and H are actually equal to F. Now, look at the normalization sum. We know that the 1 is the sum of the GA, which is the sum of GA times FA, which is also the normalization sum of F. So just putting these two equations together, we get that the sum of GA minus 1 FA is 0. But now the FA are linearly independent, and therefore you can conclude that the coefficients are 0. So it follows that GA is 1 for all F. Right? This is on the assumption that these are linearly independent. Now, in the other direction, suppose that the FA are not linearly independent. So I sort of invert that. And then I have to show that I can actually make a convex decomposition. So, but what does this mean? Then there exists constants, call them XA, which are not all 0. Right? Not all 0. So that the sum of the XA FA is 0. Right? And we can assume that the absolute value of these XA is less than 1. Right? Otherwise, you just multiply with a factor. But that makes the next computation easy. Then you set GA to be equal to XA times XA plus 1. So this is always the sum over A. Right? No, sorry, there's no sum. This is what it basically has to look like. Right? We know that any kind of decomposition of the F's has to be in terms of multiples. So then it's obvious that each FA is 1/2 the GA plus HA, because this second term just drops out. It's also clear that the operators are positive because of this condition. Both numbers here are still positive. And therefore, this is a positive multiple of the FA. That means every GA or HA is positive. Now, and if you sum the whole thing, the normalization is also okay because this sum is 0. Right? So if you look at the norm, so these are good observables. They satisfy this condition, and they are not proportional to FA precisely because this is not a constant. Right? So therefore we have a non-trivial. Therefore it follows that F is not extremal. Okay. So this means in terms of, I think I showed this visualization of cubic observables. How would that look? Let's just recap that because it kind of throws some light on this sort of decomposition. So qubit case. Then the FA would be some numbers times with some vectors. So this is the rank 1 operator. And we take, so the reason to pull out this factor is that in this way, I wanted 2 here, I think, right? Yes. So the reason to pull out this factor is so that I get better normalization conditions. Right? So this is clearly, and the FA would be positive. Then the normalization requires, so then this makes the FA positive. So if I look at the sum, this is the sum twice this, well, twice the sum of the FA times the psi alpha, psi A. And if I take the trace of this thing, I get 2, because this is the identity. And the trace of the identity for qubits is 2. And this is supposed to be twice the sum of F alpha at A. I don't know what I'm going to come up with the alpha here. So this means that the FA have to be positive and add up to 1. Right? So So the Bloch sphere picture for that is the following. So each psi alpha is a pure state. Right? It's a density operator of a pure state. That's we computed that those are the pure states. So these are the surface points. So there would be some psi 1 would be a point here on the Bloch sphere. On the outside, right? There would also be a point here, that would be psi 2, and there would be more around the place, right? So I didn't say how many outcomes there could be, like 1,500 maybe, right? So, so what this condition says, the normalization condition actually says, if I divide that by 2, then actually the convex combination of these points, so FA are now the coefficients of a convex combination. That was the reason for this factor 2. Right? So then we have a convex combination of these points. So maybe here's the point 3, and there's a point 4 somewhere, maybe here in the back. Then I can make a picture that where you can't see anything at all. But in the hand-waving version of it, there would be, you have a sphere. You have maybe 4 points, or maybe more. And the condition is actually that the 1/2 identity, which is the center of the sphere, in the Bloch sphere, that's a chaotic state, that this is in the convex hull. And given these points on the outside, you have to find the coefficients that give you, some coefficients that give you the center. Right? So first of all, if you look at the polyhedron that is spanned by these points, it has to contain the center, right? Otherwise you can't make it observable. Okay, so that's the easy part in some sense, but already if you have only 2 outcomes, what can you do? If you have only 2 outcomes, that means that on the line connecting 2 surface points, you must have the center, which means that they have to be antipodes. So if you have only 2 outcomes of a qubit measurement, and it's one of these finest ones. So then it's clear that you have to have a projection valued case because the outside points correspond to projections. Now you could also have a triangle, but the triangle again has to go through the center. When you have 4 outcomes, it's relatively easy to satisfy that. But if you have a non-degenerate tetrahedron, then actually, because this is a simplex, I talked about simplexes a little bit, or simplices a little bit the other day about classical state spaces, then these weights will be unique. Actually, 4 points just on the Bloch sphere are precisely such a linearly independent set. Now, if I throw in a 5th point, I will have some freedom of how to choose the f's, and the resulting observable will no longer be extreme. So that if you decompose a given observable into extremal ones, it will happen that only 4 of them can be non-zero in each observable that you that you use for the decomposition. Okay? And also if you have 4 outcomes, but you have a degenerate tetrahedron, that simply means that the 4 points are in a plane. Then you're basically back to the to this 2-dimensional case where you had a triangle, but now you have a quadrangle, right, in the plane. And again, the coefficients aren't unique, and you see that you have a non-extremal case. Right? Again, that means that these 4 points will not be linearly independent. Okay, so this is the basic story of the extremality. Are there questions about that? Okay, so we now had extremal states, extremal effects, yes/no measurements, and extremal observables of a sort. Not all of them, but at least the finest ones. Right? Now, how do we get the channels? That's the third element that always plays a role. And so there we actually have to think seriously about the positivity also. We had the positivity condition that we stated already was complete positivity. So we have a new cone. Right? Completely positive maps add up as completely positive maps. Right? So the sum of 2 completely positive maps is completely positive. That's this immediate from the definition. So they form a cone. But what is this cone? What does it look like? Right? What features does it have? It turns out it's sort of the same cone. And I find that very surprising. But let us make this more precise. So complete positivity was a topic that was not started by quantum physicists, but by some mathematicians working in operator algebras. So Efros was one of the senior guys there, and then fairly young guy, Manuel Choi. They started the theory of complete positivity. And, well, actually, this was, I think Steinspring was a little bit before them, in the 50s. At that time, there was no connection with the quantum physics community. And then actually, when the very influential book by Brian Davies on quantum theory in open systems, it was called, that appeared in 76. And in 76 still, Davies would say that, well, this complicated condition of complete positivity, we probably don't need that. Let's just use as a general assumption the positivity of the channels. Right? And I think this was a bad miscalculation. Right? So he was quite wrong about this. As wrong as you can be about making basic assumptions. One is, there are 2 reasons. First of all, if you look at the mathematics of the cone of positive maps that are only positive but not completely positive, almost nothing is known. We don't know the extreme rays for that cone. But it's pretty hard. Right? There are very many open questions about the cone of positive maps. Whereas for the completely positive, the theory is completely smooth. We'll finish that in this lecture. Right? So the theory of complete positivity is it is a condition that may look a little bit more complicated to state, but it makes mathematical life way easier. But this is only part of the story because, of course, we are physicists, right? So it could be that sort of the conceptually correct definition is the one that is harder to handle mathematically. But that's also not the case. Right? Actually, a good definition for channels, I gave an axiomatic definition. Right? If you want something that works in the context of other stuff being around in the world, then you should go for complete positivity. So this is a very natural physical condition. And without it, actually, it's very hard to do anything reasonable. So complete positivity is extremely important. Now, I claim now that you already know basically everything about the cone of completely positive maps. And that, of course, I have to explain. So I think there was a number for that, sub-number for that chapter. 1, 2, 3. Let's go. So this is this is named after Choi and the Polish guy, Jamiokowski. Isomorphism. This will tell you that that the positive cone of the cone of completely positive mass is just another one of those positive cones that we already looked at. And so it's named after two people who most certainly didn't know each other at the time that this was done. Jamiokowski is now an elderly gentleman, physics, I think he's in physics in Toruń in Poland. He basically messed up the point of this isomorphism. He established the isomorphism, but sort of got it wrong. Up to a transpose, actually, he got it, which means that this simple characterization of complete positivity, which is the only interest we have for this lecture, is wrong in this case. Right? You have to first transpose every map, and then it's okay. But Choi got it right from the outset. Got this. I mean, he was interested in complete positivity, so he got it right immediately. So how does this work? So here's the basic picture for it. Now, T is a channel, so it maps, let's say this is the input Hilbert space, this is the output Hilbert space, right? As before. So it maps operators on that space into operators on that space in the Heisenberg picture, or states on that space into states on that space in the dual picture. Here I put an appropriate pure state. I'll say more about that. Now, there is, so you can look at this whole thing, and this is again a version of H in. If I was really picky, I would write it as H in bar, but it's basically the input Hilbert space. Now, you can look at the outgoing state, call this rho T. And the first claim is that there is a one-to-one correspondence between the T's and the rho T's. And then we'll look at the properties of that isomorphism. So this is basically already the isomorphism. So T, this is a one-to-one correspondence. For that you have to do the right thing here. Right? You have to choose the right kind of sigma. And the right choice of sigma for the moment. So sigma is a pure state. And omega is a sum from, let's say, I from 1 to the dimension of the input space. And so it's a basis of the input space. And then we have some constant Ci, which I remind you just means that it's a tensor product of the basis vectors. Right? This is the shorthand notation for this tensor product. Okay, so this is a vector, and the only condition that we require is that these are non-zero, and you might as well take them strictly positive. This is the theme that will come in later. Also, this is also called the Schmidt decomposition of a pure state, and this will be a topic in some later lecture, but from the moment we just need that these are positive. Now, okay, so why is that an isomorphism in that case? Well, let's look at the matrix representation of that. Right? Let's expand everything in sight. So we have basis vectors I here, and here we have basis vectors, let us use small Greeks. Right? So I could look at the following. What numbers do I have to give you in order to characterize T? That's one question. And basically, well, this is going to be an operator in the outcome space. Ah, wait a minute, I should do it the other way. Yeah, let's just compute what that is. Let's just compute this thing. Sorry. We'll come to that. This is the aim, right? I'll show you that the state here, the state rho t, or this object rho t, contains all the information about t. Right? That's our first step. So let's just compute the expectation of an arbitrary operator. So an arbitrary operator can, of course, be expanded in the spaces. Right? So I would look at, in the first Hilbert space, I have the ij basis and the alpha beta basis. Right? So any operator on the outcomes of this combined system can be expanded in such operators. So if I give you all these numbers, I've completely specified rho. Right? So, but now we know what to do here. So this is this state comes about by acting on one half of another system with this particular channel. Right? So this is the trace of sigma, expectation value in that state, and you apply the identity tensor T to this operator. Right? Okay? So identity is this part, and T acts on the alpha betas. So I only wrote it out more explicitly. So this is the state rho T, basically. Right? Not basically, just exactly that. So this is the sum, this is trace of sigma. Now these tensor products act factor-wise. That's the definition of the tensor products of positive maps, or any kind of maps on the operator spaces. So it's ij tensor T of alpha beta. Now I put in the sigma. Right? So this is actually just omega, this operator, and another omega. Right? Sigma is this pure state belonging to that vector. Now let's plug that in. The vector has these constants, little c in it. So this is the sum over k and l. Ck, well, I maybe put a bar, cl. And then I have k, r and j, tensor t of whatever was there before, and then l. Okay, so this actually, I think I should factor that explicitly so you see better what's going on. I'm putting a complex conjugate here just out of basic reflexes, right? So this is a factor I pulled out of a bra, and therefore I automatically put a bar even though it's not necessary, right? So this is because I said they are positive, but actually at this point you see you don't have to choose them positive. It doesn't really matter. You'll see in a minute they have to be non-zero. So this is this is k tensor k, this is l tensor l. So I can split that and I get a k I j l from the first factor, and from the second part I get k t of alpha beta l. Now I can do the sum because this is of course a delta ik and this is a delta jl. So all along the k and l were sort of fixed to be I and j, so let's just plug that in. So this is ck is equal to I, right? So this is ci bar cj. I t of alpha beta. Okay, let me just erase one board. So. So let me just continue under this. What did we actually compute? So let me just summarize that. Trace rho t, or let's we can just write out the j beta rho t I alpha, right? So these are all the matrix elements of rho, right? And this is equal to ci r cj times I t of alpha beta j. So in other words, the coefficients that I need to describe rho t are in one-to-one correspondence with those that I need to describe rho t. Right? So these are, when I and j run over whatever they have to run over and alpha beta do the same, then I get all the matrix elements of rho t, complete information about rho t, and here I get all the matrix elements of t. That is, I can compute from that what happens to an arbitrary operator by expanding in alpha and beta, and the result I get expanded in the ij basis. So this shows the one-to-one correspondence, and all I need for that is that these coefficients don't mess things up. I can write it on one side or the other. It is actually customary to take the maximally entangled state at this point, and that is to you choose the ci all equal, namely equal to 1 over the square root of the dimension, which you need to make it normalized. Or just equal to 1, actually. That's also a common choice, but then sigma is not a state. Right? And then, so people tend to tell you that if you go to infinite dimension, there is no Choi-Jamiokowski isomorphism. But that's actually wrong. Because if you don't insist on these guys all being equal, then you can very well do that in infinite dimension. Right? They just have to go to 0 so that the sum squared of the ci's is finite. Right? So you can easily do this in infinite dimension. Of course, this whole isomorphism now depends on the c's. And we'll have to check that what is interesting about the isomorphism, namely the positivity statements, doesn't really depend on the value, on the choice of c. Right? Okay, so properties of this isomorphism. So this is what I showed now is the one-to-one correspondence, but properties of this correspondence. And I should really say these are the first properties of this correspondence. There will be more to come, actually. For example, behavior with respect to symmetries, behavior with respect to partial transposition or transposition, and many other things. So this is actually, this isomorphism is used all the time. So let's just start with a few basics. So if T is completely positive, then it follows that rho T is positive. Now this is completely obvious from the picture. Because by definition, complete positivity means that identity tensor T is a positive operator. So you're actually acting with a channel on sigma, and the outcome has to be a state. Right? Then T normalized well, then you put the identity, you're measuring the identity there, but a T of the identity, if T of the identity is 1, then you're actually looking at the partial trace of sigma of the other state, right? So that's the only remaining part. And you can just, or if you just want to plug it in here, this is actually equivalent to trace rho T is 1. Right? So in other words, is that correct? Let's check it on the equation, right? So there could be factors here, and I have to be careful. So let's look at the trace of T. What is that? The trace of rho T. I get that by putting alpha equal to beta, first of all. Right? And so let's just compute this. Trace rho T is the sum on I and Ci bar Cj. Oops. Well, I take the diagonal, so it's Ci absolute squared. Okay. And I am also summing on alpha. Alpha is equal, and then I look at I, T of alpha J, I. I put J equal to I, right? Now, this is, you can do the sum on alpha inside here. This is the identity. Right? So you just sum all the one-dimensional projections. So this is the same as the sum over I, C absolute squared, I, T of 1, I. So read this as a convex combination of these numbers. So actually it's wrong, right? So the statement that I made is wrong. It needs an additional condition here. So if this is sort of a subnormalized version of a channel, that is, these coefficients, these things can be 1 at most. Now, if the trace is 1 and this you hit the 1 here, then all of these individual guys have to be 1, which means that T actually has to be equal to 1. Right? But you can only make this conclusion if you have a little bit of extra information. So actually, I remembered it that way, but that was wrong. If you have nothing else about the positivity of T, then you can, just from this equation you cannot conclude this. You also need some that T of 1 is less than 1, and then the conclusion works. Right? But that's a standing assumption we are making anyway, so I may be excused that I confused this. So then it's better to change. Okay, so these are easy things. Now comes an important one, which is the question, when is this actually a rank 1 operator? So what can I conclude from that? So rho t equal to psi. What follows from that? Right. So if I actually could this ever be a pure state? The thing that I get out. So let's check that. Right? So then I get j beta psi I alpha. Let's make nice brackets here. So this would be Ci bar Cj on T of alpha beta J, and I want to write this as a product. So you see that the I and the alpha belong together somehow, right? And let's introduce an operator. K, and K goes from H in to H out. And you want that Cj of K applied to any basis vector J beta part is here. I want to interpret this. Basically, I want to associate this guy with a K. Okay, let me. Sorry, I have to work this out a little bit. So K is sum of J and beta. I want the beta out here because it's an operator to H out, and a J here. Right, so it's an operator between two different Hilbert spaces. So this will be a bra from H in, and this is a catch from H out. And I take Cj minus 1, that's invertible, and the psi. Or if you wish, and you express that just in a scalar product, a little bit like that other formula, I would say that beta K J is the same as Cj J minus 1 J beta psi. This is another sort of partial transposition that we're doing here, right? So I'm reinterpreting the matrix elements, or the components of a vector psi, as matrix elements of an operator. Which means that somehow one of these indices changes sign from like that, right? Okay, so so what is the T? What kind of operator is T now? Now T is then the operator claim. T T of any x, operator x is then equal to k star x k. And you check this by taking the relevant matrix elements everywhere, right? So, okay, so let's do that. We'd have to take here's the input space, so let's take the I T of alpha beta J matrix element of this guy, right? Oh, we know what that is. I mean, we have just computed that. This is C I bar C J minus 1, and then the J beta psi I alpha. Right, this is just plugging in the T as from this general isomorphism, and we also have to see what happens when I take the corresponding matrix element on the other side. So this, of course, is I k star alpha beta k j. But now I see that with this identification, I have this stuff, the beta j stuff, and the j stuff, right? These together are exactly what I wrote, right? So the beta kj matrix element is just that thing. So there is this whole isomorphism, kind of isomorphism, is actually reshuffling, as you can also see it there, reshuffling indices from their role as vector components to operator matrix elements, and back and forth between those, right? So I'm doing the same thing more or less that I did for the Choi isomorphism itself. I'm doing now for basically one level lower for the pure states that leads to an operator, right? So what we can conclude from that is that maybe I should erase 2 points now. How much time do I have? Yeah, a little bit. So this will give us an entry in, maybe I should write the entry in this table, right? So if that, if this is the case, then Px is k star x k. Right? And this whole computation also runs backwards, so you can have something like that. Okay, so here we go. The rank 1 operators, positive rank 1 operators, on the state side of the isomorphism, right, the pure states, correspond to operations like this. Now, one of the interesting questions is, are these completely positive? I think you had an exercise about that, is that true? Or maybe not, but anyway, it's clear that the map that takes x to x star x, k star K is positive. I think we did discuss that as one of the basic corollaries of the characterizations of positivity, right? So if X is a positive operator, then it's equal to B star B, and so this is obviously just this product of the same kind. So any map like that is obviously positive, but identity tensor, this map T, identity tensor T of any map X in the larger space, right, is just the identity tensor K star X identity tensor K. Just write it out. If you multiply with identity tensor K, then nothing happens to anything in the first factor. So if you have an expansion into a set of products, or first and second factor operators, the part in the first factor never sees a transformation. Right? So because it's the identity, you just can pull it through. So if this is positive, this is also positive by the same argument. But that means, and this is for any dimensional matrix algebra, but that means that T itself is completely positive. Right? So this leads to the main theorem, which is to say that, so this is so important that I actually call it a theorem. Right? So T is completely positive if and only if rho T is positive. How do we see this? We did one part already, right? That was kind of obvious, but just looking at the picture. See above. Now in this direction, if rho is positive, you can expand it in rank 1 operators. Right? So rho T is the sum of operators of the form psi alpha, psi alpha. Because it's positive. Right? So this is a spectral decomposition, but there are actually other ways of doing it. It's not important for the moment. Right? But for example, the spectral resolution would do that well, maybe typically with a factor here if you want the psi's to be normalized, but you can absorb that factor into the psi. Right? And but this immediately implies that T, this whole isomorphism is obviously linear. Right? So the sum can be pulled through, so this just means that T of X is the sum alpha K alpha X K alpha with a star in the right place. Right? So I just use this computation now to turn any one of these parts into a completely positive operator. Right? So this is the K alpha part, and then I sum them up. Proof done. Right? So it's very simple. So we proved in passing that every CP map can be written in this form, right? So from the proof, P is CP is also equivalent to T can be written as some K alpha star. Well, maybe let's put the X there. That's a bit clearer, right? And these K alpha are called the Kraus operators. So this is named after Karl Kraus, who was a student of Günter Ludwig and then later a professor in Würzburg. And he spent a sabbatical at Texas A&M University, I think. Anyway, in Austin somewhere. And he gave a course on stuff like that, fairly early actually, and introduced this notation. Basically, it's a consequence of the sign spring theorem. Or, I mean, this is a way we sort of just prove the sign spring theorem. Okay? We'll come to that later. But he wrote this little booklet that was very popular. So many physicists learned it from that. And it was not really his invention in some sense, but he was very important in making this known to everybody. So I'm quite happy with calling it those the Kraus operators. He tragically died of a brain tumor a little bit later. Well, in the early 80s sometime. Okay. So that's the Kraus representation. And so what does this teach us? What it teaches us is that the cone of completely positive operators that we defined in the way we needed it turns out to be isomorphic to a semi-definite cone. So everything we know now about extreme rays, for example, what do we know about extreme rays? Extreme rays of this guy are exactly those rank 1 animals. So they are the ones that can be written with a single Kraus term. That's equivalent, right? So also, there's a notion of rank for these operators. How many non-zero psi alpha do you need? Well, it's the same question as how many k alpha do you actually need to represent an operator? You might be wasteful in this, right? So how do you find out? Well, write your operator. So if you have your Mathematica up and running, what do you do? Right? So you have some channel, and that is given to you in Kraus form, and you are suspecting that maybe you cannot, you might simplify that representation. Well, you translate that back to vectors, which is actually no work, right? Because there's a direct formula for what to do. Right? You get a vector on the product space, but just reinterpreting your matrix elements as vector components. Right? So then you write out this operator, and in order to find out how many terms you need here, it's a good idea to diagonalize. Right? So you diagonalize this operator, you get a possibly smaller number of terms here, and you translate back. That's the way to do it. Right? So this Choi isomorphism is used all the time to do things like that. Right? So it transfers a lot of structure. And I wonder how much of that we should do at this moment. I think some of the things will be later of interest later in the context of entanglement theory. So that's fine. Okay. So are there questions about that? So one of the things that we can translate in this way are symmetries of the states or of the channels, and therefore it's helpful to talk about the symmetries of the positive cone. We're still in this chapter on the positive cone, and so let's say a few things about symmetries. So 1, 2, 4. Okay, so we know that if you have a positive operator, then you just saw that as even completely positive. Then S star A S is positive, and so that if S is non-singular, that is invertible. Let's say invertible. This is an isomorphism. So an isomorphism it's a linear operator. Let's say let's call this phi. So phi is an operator from B of H to B of H. Right? And you have a property that phi of A is positive if and only if A is positive. So that's what you call an order isomorphism. And the one direction, this direction is true for every S. But for this direction, you use the same property for S minus 1. Right? If I write S minus 1 star and S minus 1 at the end, then I just get my A back. Right? So it's clearly, when S is invertible, this kind of operation is invertible as well. And both directions will be positive operators, and this is why actually the positivity under such a map is equivalent to the positivity before the map. Okay, so this gives us quite a lot of symmetry for the cone. And but one question is, one statement is, these are not all the symmetries. Wait a minute. Yes. So can anybody think of something else? What else can I do to operators? We want a linear map, right? This is that has this property of giving a positive result if and only if the image is, the operator is positive. Any candidate? One that is actually, of course, yeah, okay. Well, one other possibility can also use phi of A equal to A transpose. This is supposed to be the transpose. And now the transpose is an operation, so every time you use a transpose, there should be, like, it's a little bit like one of these reflexes, that whenever you try to divide by something in your computation, a little coprocessor should go on in your brain and say, well, what if this is 0? Right? So whenever you do an analytic computation on paper, you should develop this reflex and say, well, wait a minute, I'm dividing here. Can I do that? Right? So in the same way, what was I saying? I wanted to give you a similar check. Right? Yes, the transpose. Whenever you use a transpose, a similar rule now. Whenever you use a transpose, keep in mind that the definition of the transpose depends on the choice of a basis. So of course what you mean is that a transpose matrix element, this is the matrix element of the transpose, this is supposed to be exactly I-A-J. Now this is one of these relations where all the matrix elements of A transpose are determined in terms of these, right? So this is a one-to-one correspondence, clearly. And you can also see that this is a positive map. Right? We actually computed already, we checked already that this is not a completely positive map. Right? So this was the basic example of a non-completely positive map. But you see here that it's a well-defined map. Right? You get the matrix elements of the image completely from that. But in writing this, you see that it depends on a basis. Right? So this is basis dependent. So whenever you use a transpose in a computation, be aware that whatever you do there is actually depends on the basis that you happen to be using. And, well, okay. Otherwise it's just mistakes. So, but anyway, once a basis is fixed, this is a good operation, and it's also clear that it maps positive operators into positive operators. It has an inverse, which is itself. Right? And so more generally, can take phi of A to be S star A star S, where S is, let's say, conjugate linear. So if you look in books, most of the time it's called anti-linear. Anti-linear is a bit unfortunate because this is actually not the opposite of linear. Right? It just means that S of, let's say, lambda phi plus psi is lambda bar plus phi plus psi. So the sums are fine, nothing funny with that, but every scalar factor is pulled through with a complex conjugate. So I put a funny star here, and the reason for doing that is that if I don't do that, then this side of the equation will be conjugate linear in A. So if I multiply A with the factor I can pull this through here. S star is also anti-linear, right? So I get a minus I here, but here I would get an I because phi is supposed to be linear. But if I put the adjoint there and I apply this to IA, then I get a minus I for the star and a second minus sign from going through an antilinear operator. Right? So I should also say what is the adjoint of an antilinear operator, of a conjugate linear operator. You have to think also a little bit to make this work. Well, you just have to check which parts of your equation that defines the adjoint are linear, and in which arguments the equation is linear, and which arguments it's conjugate linear. So the basic definition of the adjoint is, of course, I have to specify all the matrix elements. Right? Now, for a linear operator, this just means that you pull this S over here. Some people in German say überwälzen. Wälzen, I like that. Okay, so anyway, you roll it over. But this would be problematic now, because this expression is actually conjugate linear in psi, because it's the first part of the scalar product, and it's also conjugate linear in phi. And therefore, if you move this over, this would become linear in phi, and the equation couldn't be right, because it could not also be true for phi, at the same time be true for phi and for I phi, but it should be true for all phi's, right? Including I phi. Therefore, the proper definition of the adjoint of an antilinear operator is to say that this is, phi S psi. Right? Or you could also take the usual definition, which is S psi phi, and put a complex conjugate over it. That also works. Right? So it's the same. Of course, these two are the same. Right? So, but you need this extra complex conjugate because you've messed with scalar multiplication, right? And then you have to just phrase things in such a way that the equation has a chance to be right, and then it will be right. So a particular case, let's first do this. The conjugate unitary. Right? Those are operators. So in this case, S would be conjugate linear, and you would have S star S is equal to the identity. Now, if you multiply two conjugate linear operators, you get a linear operator, obviously, because you pull your factor lambda through, get a lambda bar, then you pull it through again, and then you have your lambda back. Right? So the product of two conjugate linear operators is obviously linear. So, and this is what unitarity means in that context, right? So this actually means that if you apply it in a scalar product, unitarity means that scalar products are preserved. Now this couldn't be right because in this case, because psi is in this equation is an anti-linear argument. If you multiply this by I, you get a minus I out, right? So it could be that the scalar products are preserved, but of course what could be, let us just apply the definition of the adjoint. So I'd have an S star S, and I have to also swap, or let me take this definition where I just put an additional conjugation. Right? So this is the fastest way to do it, I guess. And if that is the identity, then of course you just get phi psi bar, or if you wish, you can write this as psi phi. So you also exchange the order, or you could say you get an additional conjugation. Okay. Now, why am I saying this? Transposition, I claim, is of this kind. S phi is phi bar. This is complex conjugation. So you have a wave function, and you just take the complex conjugate of every value of the wave function. Again, the same warning. This is obviously basis dependent, because what it really means is that S of a linear combination that you could write. I shouldn't take J. Let's take J. Right? Of course, if you're in electrical engineering, J is I. They write J for the imaginary unit. So. Anyway, you don't. So this is fine. So because this is a conjugate linear operator, so this just means take complex conjugates of the coefficients. So this would be sum j, cj bar j. So this is the definition of complex conjugation. And again, you can see very clearly that this is basis dependent. So, but it's actually the same basis dependence that the transposition operation has. So let's look at, so this just means that that Sj is equal to J. So you've picked a basis which is declared to be real. Real in this case means it's invariant with a complex conjugation. So relative to this operator S of complex conjugation that I defined before, there are some vectors that are clearly independent of this. Of course, everything that has real coefficients here is invariant, but also just the basis vectors. And once you fix the basis vectors that are real, that are invariant under S, of course you know the whole thing. Right? So let us look at S star, A star, S, a general matrix element, call it J, K. Okay? Well, what could this be, right? So S is actually, S acting on J gives nothing. Well, now this is a computation in the basis that for which S is real. Or is, no, which is take a real basis, one with this property. Okay? So this is something that we now use in this computation. Okay, so the Sj stays unchanged. So you basically get K S star A star J. Well, let me write this as basis vector Ej. I want to sort of conjugate it more nicely. Ek. Or yeah, no, that's okay. Sorry. Kj as before. Now, if I put the S star on the K, of course K is invariant under S, but when I roll over an anti-linear operator, I also have to swap the order of the factors or put an additional complex conjugate. So let's do that. So this is K A star J complex conjugate. But you know what the complex conjugate, what the star does, right? You can actually put it here. And this is, a star puts a conjugate and a transpose, so this will be J. Okay. So this is actually equal to K A transpose J. So in other words, this operation, so the transpose is implemented by a map, not a unitary map, but a conjugate unitary map. Right? So there are some symmetries of this cone that are not given by, and actually you can see that every anti-unitary or anti-linear and invertible map defines a symmetry of this cone. Right? I mean, maps the cone into itself. And I think I'll stop here because I need a little bit more time for the converse, which is also true. This is called Leibniz theorem. Okay, good. Then I'll see you tomorrow. Huh?